Namaste. Welcome to the Indian Knowledge Systems primer course for children. In the series of lecture on Indian astronomy, in this session we will look at the revolution of Earth, its tilt and Shadrutus. Shadrutus are the 6 seasons. Very interestingly, in the Indian astronomical tradition and various other astronomical traditions, we used to follow the geocentric model, wherein the earth is considered as the center and everything else is considered to be revolving around us. This was a natural model to come to a conclusion to, because when we look at the sky, we see all the celestial bodies rising and setting, and this sort of when looked at in a glance, that it sort of makes us understand that it's all revolving around us. So this geocentric model was widely adopted earlier. Today we know that the heliocentric model, where the sun is the center and all the celestial bodies revolving around the sun or the planets revolving around the sun, is true. However, we must understand that the word model is actually a way to capture the reality. Especially it might reduce or it might minimize various dimensions of the reality, but it tries to capture some critical aspects of it. So the geocentric model was sufficient to make observational astronomy happen. We could observe planetary motions, and we could also do Digdesha Kala Nirnaya, which was the primary objective of Indian astronomy or Jyotisha. We could discern various nuanced aspects and compute and predict the various celestial happenings pretty accurately. So, to summarize, the geocentric view necessarily saw Earth as the center of the universe with all the celestial bodies, including the sun, moon, the planets and stars revolving around it. This model was developed by astronomers that were prevalent at that time, both in India and other parts of the world. Though the model is now not to be seen as very true, it served as a means to study the motion of celestial bodies and calculate their periodicities as well. Among the various astronomers who have tried to understand and model planetary motions, in India there has been a wonderful astronomer called Neelakanta Somayaji, who belongs to Kerala School of Indian Astronomy. He had made significant contribution in this field specifically. There were various schools of Indian astronomy and different regions were actively pursuing this body of science. In Kerala, there was a live tradition which seemed to have been pioneered by Madhava. He hailed from the place called Sangama Grama during the period of 1340 to 1420 CE. Madhava is a genius in Indian mathematical and astronomical traditions. Coming in his lineage was Neelakanta Somayaji. He hailed from Trikantiyur from around the time period of 1444 to 1550, which is roughly about mid 15th century to 16th century. He has done monumental work in both mathematics and astronomy. Especially in astronomy, his work called Tantra Sangraha has been thoroughly studied and well published, and its relevance has been brought forth by very important researchers and professors of our country. Neelakanta Somayaji, of the many contributions that he has done, one among the phenomenal contributions is his revision of the traditional planetary theory. He carefully studied the planetary motion, because in Kerala tradition they also have this practice of having collected a vast amount of data. So he created a unified model where he showed that, as you can see here, the point O in the diagram is where the earth is or the observer is. As per this model, the sun revolves around the earth. But the five other planets namely Mercury, Venus, Mars, Jupiter and Saturn, all of them revolve around the mean sun in an eccentric orbit. What is an eccentric orbit? We will define it a little later. This model is the closest the Indian astronomers have come to the Keplerian model, which evolved a century later in the West. Around the same time when Nilakanta Somayaji came up with his model, in the West, the heliocentric model transition was also happening. Copernicus at first proposed this, which Galileo at the end of 16th century adopted it, roughly around 1590s. Later, this became very popular, where Tycho Brahe and Kepler built upon this and made various astronomical observations. They then arrived at the famous Keplerian planetary laws, which are well known right now among higher standard physics students. As you can see in this picture, according to the heliocentric model, the sun is in the center, the earth revolves around the sun, the moon revolves around the earth and around the sun, and all of these revolutions happen in the anti-clockwise direction. So, it is good to know the heliocentric model as well in order to appreciate various astronomical phenomena, because and also the evolution of ideas in Indian astronomy. So, now let us try to understand what is the time taken by Earth to revolve around the sun. We commonly study in our schools that the revolution time period of Earth around the sun is about 365 and a quarter day, which is actually an approximation. To be precise, Earth completes one revolution around the sun in its orbit in about 365.2422 mean solar days. A mean solar day is a term used to refer a 24-hour day, which is the average length of the day. This time period, this 365.2422 or 242216 is also called as a tropical year technically. So, this is the exact time the Earth actually takes to revolve around the sun. So, we need to sort of go around a full 360 degrees around the sun, and for that we take about 365.2422 days. If we calculate what is the angular movement that the Earth covers in a day, it is only about 0.986 degrees each day, which seems very negligible, but over the course of the year they slowly add up and the Earth sort of completes an entire orbit around the sun. This is why we see there is a gradual change in the position of the sun in the sky over the course of a year. Actually, this is how do we observe this? We will see that in the coming sections. In fact, this is what causes the seasons and its transition also during the year. So, let us try to understand the orbit of the Earth. The orbital path of the Earth around the sun is elliptical and not circular. In a circular orbit, the Earth will be equidistant from the sun all through the orbit. In an elliptical path, that will not be the case. So, there are 2 points of significance in an elliptical path. One is the perihelion point, which is the closest point of Earth from the sun, which measures to 14.7 crore kilometers. And the other point is the aphelion point, which is the farthest point of Earth from the sun, which measures to 15.2 crore kilometers. So, how much is the difference between the distance of these 2 points? It is about 0.5 crore kilometer, which is 50 lakh kilometers, which seems like a huge distance. But when you see the scale of things in the outer space, it is not much, because the eccentricity, if you see, is only about 0.016. Eccentricity is a value which informs us how much an orbit is not a circle. For example, if the eccentricity is 0, then the orbit is a perfect circle. If the eccentricity is 1, then the orbit is more a linear line. So, here the eccentricity is only 0.016. So, sometimes when we draw these orbital paths in our notebooks, we draw it way too elliptically. This elliptical nature of the Earth's orbit contributes to slight variations in the length and the intensity of the sunlight that we receive throughout the tropical year. Moving on to the next slide. We have seen the nature of Earth's orbit in the previous slide. Now let us understand about the axis of Earth's rotation. So the Earth's axis is actually tilted with respect to the plane of the orbit around the Sun. What does this mean? Let's assume that this is the Sun. So what did we see about the orbit? The orbit of the Earth, this is Earth. So the orbit of the Earth is elliptical, which is like this. It's not a perfect circle. So there is a aphelion point and there is a perihelion point. So it sort of orbits the Sun like this. But in this path, the Earth is not rotating and revolving perpendicular to the Sun, as in it's not like this. The whole Earth sphere is slightly tilted. And this tilt, the angular tilt of the Earth with respect to its orbital path is about 23.5 degrees. So it sort of rotates like this and revolves around the Sun like this. Okay. So this is called as axial tilt or obliquity. So the Earth spins, but the spinning axis is not perfectly perpendicular to the plane of orbit. Currently the measure is about 23.5 degrees. This too can change over thousands of years. Earth's tilt actually has been changing over the time. It has been varying approximately from 22.1 to 24.5 degrees. Over 41,000 years or so, it is said that the tilt varies between these 2 points. Ancient astronomers also had discerned that the axial tilt was present in Earth. Especially in Indian astronomical texts, the estimate of the tilt was given as 24 degrees, which is pretty accurate considering the modern measurement of 23.5 degrees. Especially we will have to see that these were derived at using thorough calculations, and the calculations were made during a pre-telescopic era. So we did not have such sophisticated instruments. They still were able to arrive at a pretty accurate angular tilt measurement. This axial tilt is very important because it influences the intensity of the sunlight that reaches different part of the Earth throughout the year. This is what also causes the seasonal changes.
We all know that the earth goes around the sun. When we closely observe the earth has a certain tilt with respect to the orbit in which it is going around the sun. This tilt is not perfectly 90 degrees with respect to its orbit. Now it is 23.5 degrees. Ancient Indian astronomers approximated it to 24 degrees. Actually, the tilt keeps changing with time, and it happens that currently it is at 23.5 degrees. Now let us observe in this animation different facets. I've positioned an observer on 10-degree latitude on Earth. This is the equator, that's the Tropic of Cancer, and this is the Tropic of Capricorn. That's the Arctic Circle, and this is the Antarctic Circle. And you will see that the angle of incidence of light from the sun changes as we go around the sun. Now we are in February 10, and if I start this animation, we are slowly going around the sun. Now we are reaching a point in March where this tilt is not making any difference to the way in which we receive the sun. So the northern and the southern hemisphere receive equal amount of sun. If we move further from March, we will see that as time goes, the northern tilt makes the northern hemisphere to be closer to the sun, whereas the southern region is quite far away from the sun. Now, it happens that on this particular date, the southern hemisphere, right, this tilt is more tilted towards the sun. And this happens around June 21, where the Earth, the northern hemisphere of the Earth, is receiving a huge amount of sunlight. And within the Arctic Circle, it's fully day. This aspect leads to the northern hemisphere getting more sun as well as having a longer day duration compared to the night duration. Whereas the southern pole is fully in darkness at this point in time and there is no light. Hence, this angle of tilt, the axial tilt of the earth, makes a huge impact as we revolve around the sun. The revolution around the sun happens in about 365.25 days. And how would we know we have finished revolution around the sun? In the next set of simulations later, we'll understand that. But now appreciate that the tilt of the earth slowly determines the angle in which or which hemisphere of the earth is more closer to the sun. Here we see that around this time, the southern hemisphere is more closer to the sun and not the northern hemisphere. In fact, on the 21st of December, we see that the northern pole is fully dark and beyond the Arctic Circle, it's fully night. And here the southern pole is fully exposed to the sun. So the southern tilt, the southern hemisphere, has more access to the sun. Thereby, the seasons keep changing, and the season in the southern hemisphere right now is summer, whereas in the northern hemisphere it's winter. And this, as we go around the sun, the angle of incidence makes a huge difference. Here we have the summer solstitial time. Here we have an equinoctial day in September 21, where we see that the tilt of the earth has no bearing on how we receive the sunlight. So the northern and the southern hemispheres receive equal amount of sunlight. So this is an equinoctial day where the duration of the day and night is the same. Whereas when we come here to about December 21, we see that on that particular day, we will see that the southern hemisphere to receive the most amount of sun, to be most closer to the sun, whereas the northern hemisphere is the farthest away from the sun. Hence, the tilt of the earth in a combination with how we revolve around the sun decides how we experience seasons on earth and also helps us understand how on different locations on earth we might experience different seasons.
As we saw in the simulation, the tilt of the earth plays a significant part and impacts the exposure of the sun on different parts of the earth. This diagram captures the equinoxes and solstices for people in the northern hemisphere of earth. As you can see, during the equinoxes, the tilt does not impact how the sun rays are received in earth. The earth's axis is not tilted towards the sun during the equinoxes. The point, the central part where the earth is shown, top and bottom of the sun, that's the equinoxial point. Equinoxes occur twice a year, once around March 21st, which is called the vernal equinox, and once around September 21st, which is called the autumnal equinox. On these dates, the duration of day and night are equal in length all over the world. Solstices occur twice a year, around June 21st, which is called the summer solstice, and around December 21st, which is called the winter solstice. This is for the northern hemisphere. The reverse will happen for the southern hemisphere. The summer solstice is the longest day and shortest night of the year in the northern hemisphere because the north pole will be tilted towards the sun by then. Hence, it receives a lot of sun rays. Conversely, the winter solstice will be longest night and shortest day because the north pole is again tilted away from the sun. As the earth's tilt gradually impacts the exposure to sun, as we slowly revolve around the sun, we experience the different seasons on Earth.
In this simulation, we will look at how the tilt of the earth affects how we view the sky. I have positioned myself on the 21st of March 2024 at 6:31 am. The sun seems to be rising here in the east. And as time goes, the sun comes up, and at around 7 am, the sun is here. Now at 7 am on 21st, sun is here. If I were to keep jumping the date at the same 7 am and observe the sun from the same spot on earth, you see a mild difference 22nd, 23rd, 24th, the sun's position is mildly changing. And as the days go, the sun's position keeps changing quite a bit. This is because of the tilt of the earth. On the 21st of June, it goes all the way up till here. When we are in the orbit around the sun, the northern hemisphere gets exposed to the sun the most on this day. And as time goes, slowly the southern hemisphere gets more exposure to the sun, and thereby the sun seems to be having a southward run. Every single day, the sun seems to be moving a bit more south, and it goes all the way till the 21st of December to the southernmost point that the sun can go. Now we are at a point around the orbit of the sun where the southern hemisphere has the most exposure to the sun. So, for the people in the northern hemisphere, it looks like the sun is quite south of east. And as time goes, the sun now slowly starts coming up day by day at the same 7 am at a slightly northward position. And hence, the tilt of the earth plays a very, very crucial role on how we receive and perceive the sun on the earth.
Moving on to the next slide. So, the Shad Ritus or the 6 seasons. In the Indian tradition, we typically consider 6 seasons which are of the following. One is Vasantaha, which is spring. Second is Grishmaha, which is summer. Third is Varshaha, which is rainy season. Fourth is the Sharad Ritu, which is the autumnal season. Fifth is Hemantaha, which is the pre-winter season. And sixth is Shishiraha, which is the peak winter season. Now, we saw the tilt, how it impacts the season and all of that. We will now see how the seasons are actually caused. There are two primary seasons as we go around the sun. Because of our tilt, the seasons are caused. When we lean into the sun, that is when our tilt is more closer towards the sun, in the northern hemisphere, the sun hits us in a more direct angle because the earth is tilted towards the north and towards the sun. As you can see in the image shown here, consider a 1 square meter area on earth. So, when the tilt is towards the sun, the rays that hit the earth's surface will be more direct, making an angle of incidence of about 73 degrees. But as the tilt is moving away from the sun, as in the earth moves away from the sun and the tilt is also away from the sun, the angle of incidence also becomes less. Thereby, the impact of sun rays on that particular 1 square meter becomes very less. We will try to understand this using an activity. You can all try this at your home. So, use a flashlight and try to point it at a perpendicular direction towards a wall. We will all be able to see a highly intense, well lit, a very perfect round area on the wall. But if you slightly tilt the flashlight, you can see that the intensity of lighting of the area will become a little dispersed. This is because of the tilt. Similarly, during June, when the northern tilt, or when the northern axis is towards the sun, the area that gets the sun rays will have a high intensity sun rays. But at the same time, when we move towards winter, the area that gets lit will not have that level of a high intensity, because the tilt of the earth is away from the sun. The second factor that impacts the season is the length or the duration of the day. Across a year, the length of the day varies. For example, on an equinoctial day, the length of day and length of night will be equal, while on a solstice, the length of day might be higher and the length of night will be lesser if it is a summer solstice, while on winter solstice, the length of night will be larger than the length of day. So, this is how the tilt of the earth plays a huge part in how we experience our life on earth. We will also continue to understand more insights from Indian astronomy in the upcoming lectures. Thank you.